Welcome to The Explainer. Today, we are breaking down something you feel every single second, but maybe don't fully understand: temperature. We're going to go on a journey from that simple, and often pretty misleading feeling of hot and cold, all the way down to the invisible, buzzing world of molecules and how we finally figured out how to measure it with precision. So let's just jump right in with a question for you. Do you think you're a good judge of what's hot and what's cold? I mean, when you touch something, can you really tell its temperature? I bet most of us are thinking, yeah, of course.
Well, here's the thing. Your sense of touch is actually a surprisingly unreliable tool. What feels hot to you might feel just lukewarm to someone else, and it all depends on what you were touching just a few seconds before. You can prove this with a classic, super simple experiment. You take 3 bowls, put one hand in hot water, the other in ice water, and just leave them there for a minute. Then, you plunge both hands into the middle bowl, which is just room temperature water, and the result is bizarre. Your hand that was in the hot water now feels cold, and the hand from the ice water feels hot, at the exact same time in the exact same water.
So, what on earth is going on there? Well, the key thing to get is that our perception is all relative. Your skin isn't actually measuring temperature, it's measuring the rate of heat flow. Is heat rushing into your hand, or is it rushing out? And this subjectivity, it creates a huge problem for science. We needed an objective, universal standard that works the same for everyone, everywhere.
To build that standard, first, we have to understand what temperature really is. And the answer isn't something we can feel or see with our own eyes. No, we have to go down to the molecular level.
Here's the secret. Everything around you, me, this whole room, it's all made of molecules that are constantly jiggling and vibrating. And temperature, at its very core, is just a way to measure how fast, on average, those molecules are moving. It's their kinetic energy. The more they move, the more energy they have, and the hotter the substance is.
Think of it like this. Picture a cup of hot chocolate versus a cold milkshake. In that hot chocolate, the molecules are having a wild, high-energy dance party. They're bouncing off the walls, just going crazy. But in the cold milkshake, it's more of a slow dance. The molecules are just kind of swaying, barely moving. It's really that simple. The faster they jiggle, the higher the temperature.
Okay, so how do we take this invisible dance party and turn it into something we can actually read on a device? The key is something called thermal expansion. See, as those molecules heat up and start moving faster, they need more personal space, right? So they push each other further apart, and the whole substance expands. In a thermometer, that expanding liquid has nowhere to go but up a tiny glass tube, giving us a clear, visible measurement.
So now that we can measure this change, we need a common language to talk about it. It's not good enough to just say something is hot. We need standardized scales so that a temperature reading in one part of the world means the exact same thing on the other side of the planet.
Now, the 2 scales you probably know best are Celsius and Fahrenheit. Most of the world uses Celsius, which is super logical. It sets the freezing point of water to 0 degrees and the boiling point to 100. The Fahrenheit scale, which is mainly used in the US, marks the same 2 points at 32 and 212.
But then there's the one scientists consider the gold standard: Kelvin. So what makes Kelvin so special? Well, it's an absolute scale. Its starting point, 0 Kelvin, is absolute 0. That's the theoretical point where all that molecular motion completely stops. It's the coldest anything can possibly get. So Kelvin doesn't just measure relative hotness, it measures the actual thermal energy a thing has.
And the great news is, we don't have to pick just one. We can easily convert between all of them with some simple formulas. So that chilly 30-degree Fahrenheit morning in Srinagar, that's about -1 Celsius. And a scorching 46-degree day in Bengaluru, that's a blistering 115 degrees Fahrenheit.
All right, so let's move on and see how this all comes together in the actual tools we use every day to measure temperature, starting with that classic, the liquid in glass thermometer.
So the 2 classic liquids you'll find inside these things are mercury and alcohol, and each one has its own pros and cons. Mercury is great. It's that shiny silver liquid, super easy to read, and it works over a huge temperature range. The big downside? It's toxic. Alcohol, on the other hand, is much safer, and it can measure extreme cold, but it can't handle high heat. It just boils away.
And this brings us to a really crucial idea. Not all thermometers are created equal.
They are specialized tools specifically engineered for very different jobs, and their design tells you exactly what that job is.
Take a clinical thermometer, for example. It's designed for one job and one job only, measuring human body temperature. So its range is super narrow. But the real genius is this tiny little kink, or constriction, right near the bulb. It's a clever little feature that acts like a one-way valve, trapping the mercury at its highest point so it doesn't fall back down before you get a chance to read it. Pretty smart, right?
Now, a lab thermometer is a completely different beast. It's built for science experiments. It has a much wider range, so you can do things like boil water. But critically, it has no kink. It's designed for an instant, real-time reading, which means a scientist has to read the temperature while the bulb is still right there in the substance.
And you would definitely need a lab thermometer to measure something like Earth's hottest recorded temperature. It was a staggering 56.7 degrees Celsius, set way back in 1913 in Death Valley. A clinical thermometer would have just shattered long before it got that hot.
Of course, today we're in the digital age. Modern digital and infrared thermometers have totally changed the game. They're way safer, no toxic mercury, and they're incredibly fast. Instead of thermal expansion, they use electronic sensors for an instant reading. And tools like the infrared thermometer let you do non-contact screening, which, as we all know, became absolutely essential during the pandemic.
But here's the thing you gotta remember. No matter how advanced the technology gets, one rule will always apply. Getting an accurate scientific reading depends entirely on using the tool correctly. A precision instrument is only ever as good as the person operating it.
So if you ever find yourself using a lab thermometer, here are the 4 golden rules for a perfect reading. 1. Keep it straight up and down, perfectly vertical. 2. Make sure the bulb is completely surrounded by whatever you're measuring. 3. Don't let the bulb touch the bottom or the sides of the container. And finally, number 4, get your eye right down to the level of the reading to avoid what's called a parallax error.
So what's the big takeaway here? It's really this incredible journey we've taken, from a simple, flawed feeling of hot or cold all the way to a precise science. It's a story about creating objective tools and universal standards to make the invisible world of energy something we can all see and measure.
And that leaves us with one final kind of mind-bending question to chew on. If heat is the energy of moving molecules, then what exactly is cold? Is it a thing in and of itself, or is cold just the word we use for the absence of heat? We'll let you think about that one.